Did you know just how important fractions actually are to your children succeeding in high school level maths? Because I certainly didn't. And today I have Matty from Maths Pathway joining us to give us all the ins and outs and explain why understanding fractions well is the cornerstone to your child succeeding in high school level mathematics. So let's just get straight into it.
I'm just going to get started. So
Yes,
thanks
excellent.
very much
Thanks, Maddie.
for turning up or for watching this. So my name is Matty, and I have been teaching mathematics for a really long time now, for decades. And I'm really passionate about making sure that kids have really high quality education and end up being numerous members of society, basically. And I decided to talk today about fractions for some really specific reasons. And we'll talk about them in a second. So I'll talk about what I'm covering here. And if you have any questions, please put them in the chat, or I will give you an opportunity to talk to me about them later on. So the first thing is, why even bother talking about fractions specifically? And I have some data to show you. And it might not necessarily be your student, but it gives you an idea of what the problem is generally. So worldwide, it is actually a problem that students have a lot of gaps in fractions. They have a lot of misconceptions. And so I want to make you guys aware of what those misconceptions are and give you a whole bunch of examples on how to treat them if you wanted to do it yourself. And there are quite a number of fraction models that are recommended to be used in basically the pedagogy. So when you look at the literature of how should you teach fractions effectively, there are models that you should use in certain instances, and they have pros and cons. So we'll talk about them as well. And you'll see at the end of the slides, which I'm sure Kylie will share with you, is there's a bunch of research links. And really the purpose of that is, if you want more information, if you want to find out more, please go to those links and you can find all sorts of really in-depth information on how to teach fractions effectively. So why fractions? This is huge. They really underpin the rest of mathematics. So when I say proportional reasoning, what I mean is what comes next. So topics in maths like percentages, ratios, rates, scales, similarity, and probability, they all require understanding fractions as a prerequisite. And by ratios and rates, that's also algebra is incorporated there. And they also help students build number sense. So my goal as an educator, and I'm sure your goals as parents, is to really get your students to be mathematically proficient, to be able to, for them to have enough numeracy and mathematical understanding that it doesn't hold them back in any way. And effectively, mathematics is a language. And so what they need to understand is the structure of number. And fractions is the first time that we move beyond whole numbers like 1, 2, 3, 4. We're now extending into what we call the rational number system, which includes things like fractions, but it also includes things like surds and irrational numbers, which gets more complicated, but it's the first time that students jump to that. It's also the first time that we can really explore that idea of the density of numbers, that say between 0 and 1, if we go halfway, we've got the number a half. And if we go between 0 and a half, we've got the number a quarter. So that density of numbers is really important just to understand the number system in general. And you'll see that we focus a lot on number lines, which students typically have a lot of difficulty with. However, it really helps them have a strong understanding of things like magnitude, which is the size of numbers, equivalence. So this is a thing that students really struggle with, like, the fraction 1 over 2 is the same as 2 over 4. And that whole idea of equivalence is really important in mathematics beyond fractions, right? When we're talking about algebra, for example, and being able to order numbers, which number is largest, which number is smallest. So again, this is more about number sense. And they really connect arithmetic for the first time to algebra. There's a lot of research that shows this connection, that students that have really early success with fractions, they then have really, they have a better outcomes in in algebra, because it's the connections are there anyway. There are things like algebraic fractions. If a student doesn't understand fractions, then they won't understand algebraic fractions. And the final point here is about flexible thinking with multiple representations. This is a quite technical language, but really what this means is we want students that are able to solve a variety of mathematical problems in novel situations, so in new situations. And what that really means is that you're able to tackle any sort of problem and apply mathematics to anything. And incidentally, this is a skill that employees really rate quite highly as well. There's fractions in everyday life. So for financial literacy, you need to understand fractions for things like music and recipes. So it's beyond the mathematics classroom that you need an understanding of fractions. And again, the thing that I mentioned earlier about there's a lot of research that shows that students that show success in early fraction, it's actually on stuff on number lines, it is a really great predictor of success in maths. And so why is that important? Well, really, fractions are what I'd like, to get across is that you guys should not see fractions as a box to tick. It's really, you need to make sure that your students or your kids do not have gaps and that they've really got it before you move on to anything else. Because if they don't, what happens is those gaps only widen over time, and you end up having, somebody that cannot access higher level mathematics and also STEM pathways. So careers that require maths, that includes, economics, it includes medicine, it includes engineering. So, what do year seven students typically know about fractions? So this is about, identifying the gaps so that we know what a student should know by the time they get to year seven. So this is a map of all the prerequisites, and this is based on the curriculum, on the Australian curriculum. It's very similar for the other state curricula as well. It doesn't really differ very much at this level. And so at level three, we want students to know unit fractions. A unit fraction is a fraction where the numerator is one, something like 1/3 or 1/4 or 1/5. That's a unit fraction, and then multiples to get to a whole. So for example, them being able to count, I've got 1/3, 2/3, 3/3 is what we're talking about here. They need to be able to do that fluently. Then they need to be able to show equivalent fractions. That means like if you have a bar and they, say it's divided into quarters, we need them to be able to identify, how can I, and one bar is divided into quarters and the other one is divided into halves. What's the equivalence between the notation and the bar and the model? There's fractions greater than one. So, I was talking before about unit fractions like 1/3, 2/3, 3/3. So 4/3 is a fraction that's greater than one. So them having an understanding of that. Being able to compare unit fractions. What that means is if I have a third and a quarter, which one is larger and how do I know? And then being able to add and subtract fractions with the same denominator. So how do I add 1/3 and 1/3, for example? At level six, you'll see it's really interesting. At about this level is when kids start developing really large gaps, because now we start talking about related fractions. Those are fractions that don't have the same denominator, and you want to be able to compare them. You want to be able to convert between, say, improper and proper fractions or mixed numbers, and you want to be able to add and subtract these related fractions as well. And they really rely on students understanding the equivalence of fractions. So they might look different, but have the same value. I'm only going to look at this briefly, but this is just a visual that shows you the gaps that we would be expecting a year seven student to have. So it's massive. Like these last ones here were those year six ones. So a year seven student, about 18 to 19% of them know these things, or even less. This one's at around 15%, which means that 85%, up to 85% of students that go to year seven level don't know this stuff. Like they don't know how to add and subtract fractions with the same or related denominators, which again is like my whole point. We cannot ignore this because this will stop them from achieving in later mathematics. So let's talk about some of the misconceptions that they have. And we don't have a lot of time, so I'm going to show you 9 of them, explain them briefly, and then I'm going to focus in on 3 of these. So I'll start at the top and I'll work my way. So they don't recognize that fractions require equal division of a whole. So that idea that you start with a whole number and you divide it into parts is really the definition of what a fraction is. Like how many parts out of the whole is what it is. And so they need to understand that each of the parts have to be the same size. Otherwise, we don't have a fraction. They need to understand when you add fractions, why don't you add the denominators, right? And we're not talking about procedural understanding here. We're not talking about them being able to follow an algorithm. We're talking about them understanding conceptually why this is the case. The next one here is they don't recognize that a larger denominator causes a smaller fraction part. That's what I was talking about before. So we want them to be able to compare. Is 1/3 larger or smaller than 1/4? And how do you know? They can't read fractions on number lines. So this one's interesting. 0/4, they think that's greater than 0/5. But of course, they're both 0. So this is a misconception about equivalent fractions. They know tricks. Okay, so they know procedures and algorithms to create equivalent fractions. They know how to convert mixed numbers and improper fractions, but they don't have a conceptual understanding. They don't know what that means. And that honestly is a useless skill because really, remember the point is that we want them to be able to generalize these to algebraic numbers and algebraic expressions. And so really the whole point is them not knowing the tricks. The whole point is them knowing the structure of a fraction so that they can then apply that and generalize it later on in other areas of mathematics. This one's similar about the role of the whole in defining a fraction. And then, there's actually a lot when you start thinking about it. The notation and the language about fractions is quite complicated. And so we need to spend time developing that and also connecting. So connecting the words 1/3 to the notation 1/3. So let me go to the next slide. The orange ones are the ones that I'm going to focus on. And what I'll do is I'll show you a bunch of examples that you could use that hopefully also illustrate how important and how, nuanced you have to be to make sure that you don't develop these misconceptions when you're teaching fractions to students. Okay, so this is the first one. And notice here that we're using bar models. So these here is an example of a bar model. And we have defined the whole as the whole bar. And then what we've done is we're really getting students to compare in a really visual way the differences between a half, a third, a quarter, and a fifth. When you show it this way, it becomes really obvious that as the denominator becomes larger, the size of each part of the bar becomes smaller. And so this is an inverse relationship, which students find quite tricky. So the common misconception is that they think that the larger denominator makes the larger fraction. But of course, we see here quite clearly that that's not true. Here's another example. So the previous one, if I go back to it, we had unit fractions here. The denominator is always 1, 1, 1, 1, 1. But here's a slightly more complex example where we don't have unit fractions. We've got 4/7, so this is the 4/7, and 4/5. And notice that, we are quite deliberate about the fact that we connect all the time the fractional notation with the words. And that's come out of our study of the literature and what the experts have basically told us about how we should teach fractions. You should always do that to help strengthen those connections and the multiple representations of fractions. And of course, we also have the bar model. And look how nice this visual is. It's so clear for a student to see that 4/5 is more than 4/7. And they can see really clearly that 1/7 is smaller than 1/5, right? So the larger the denominator, the smaller the size of each part. Next example. And look at this one's a tricky one. So we use this in our model a fair bit in our maths pathway, where we actually show students the misconception. So here we have Abigail, and she's saying, well, look at 1/8, it's bigger than 1/6, which is going against what I just said, right? But what we want them to be able to identify is that the whole is not the same. So Abigail's drawing is not consistent because the whole here is much larger than the whole here, which means you cannot fairly compare the two diagrams. So these are things that kids would normally do, right? They will draw, they'll casually draw the bar and they'll say, oh, so 1/8 is bigger than 1/6, but we know that's not true. Here's another great thing to do, and with your kids, is actually get them to construct the fractions. The easiest way to do this is by using a bar and paper folding. So you can very easily, just take a strip of paper and fold it once, and you'll get two parts, so halves. You can fold it easily 3 times or 4 times, or even 5 times is not that tricky. To do this with other models like circles is actually much harder for students. So this is why we recommend paper folding. And notice as well, we again are making the connection between the fractional notation and the words. 5/8 is the same as 5/8. So here we're talking about the next misconception, which is reading fractions on a number line. And we start with, you'll see this if you ever read literature on how to teach mathematics. It's one of the key things that you should always do is define the minimum and the maximum cases. And this is what we're doing in this question. So the minimum case is obviously 0. What does that look like on a number line? And the maximum case in this instance anyway, we're looking at one full lap of the pool. So that means all the way between 0 and 1. And then we also have defined halfway as a half. So, here we have the swimmer, halfway between the numbers 0 and 1. And you'll see that we'll build. So if you have a look at our modules, you'll see that we will then build on that idea. We define the smallest, the largest. And look, we're already doing that here. So the previous case, if you have a look again, the number line shows halves because we have divided the number line into 2 parts. But in the next case, we now have divided the number line into 3 parts. And again, we're now looking at the minimum and maximum case. So Kathy, she's at the start, she's at the end, she's at the finish line. And now we're defining 1/3 of the way and 2/3 of the way. So using also concrete examples, real life stuff also helps as well, which is something that we try to do. Now, recall earlier that I said that students find number lines really difficult sometimes. And so what we do is and I recommend this because they find a bar model, so this is a bar model, much easier to comprehend and understand. And so we make the connection between them. We draw the bar above the number line, and here they can see that, 2/3, that is the same length. Kathy has ran 2/3 of the way on both the bar model and on the number line as well. So making that connection. The example along the bottom is a little bit more complex because now we're looking at 3/5, and again making that connection between the bar model and the number line. And there are some other things that we do consistently with our number lines that I would encourage you to do. So this one we haven't labeled deliberately. This is 1/3 and 2/3 because it's an early scaffold. But as the students learn more and more, we add more features to the number line. So you see here that the number line is now labeled. We have each of the parts or each of the lines labeled with the fraction. And we can at times also label the 1 as 5/5 so they can see the equivalence. And of course, we look at number lines beyond 1 as well when they get to that point. Again, we're still talking about reading fractions on the number line. Now we're connecting that idea of, what's bigger, 1/5 or 1/8. And you see here, like it's really clear on this number line when you consider the context that we've used that Jumbo's jumps are bigger than Larry's jumps, and therefore 1/5 is larger than 1/8. So it's the same idea, but we're using multiple representations to connect these ideas. Here's a really common misconception about number lines. What students sometimes do is they count the tick marks. So first of all, like what you need to do is do what Jill does, which means count the gaps, and that will tell you what fraction can be represented on this number line. So if you count the gaps, you get 7. But the misconceptions come about when students ignore the 0 and the 1 and they count the tick marks in between the 0 and the 1. So Melania thinks that this is representing, or that you can represent 6 on here. The other misconception that happens is that students count all the tick marks. And so Michelle thinks that I can show 8s on this particular number line. So you have to be really careful, and you need to give students repeated exposure to these ideas and get them to point out the misconceptions and the common mistakes to try and get them to avoid making them. So this is a general kind of overview. Get students or get your kids to draw their own number lines, and get them to connect with different types of examples and to read different types of number lines as well. So the next misconception was about defining the whole. And here we have a new model. This is called a collection model. And it has pros and cons, which I'll talk about briefly later. And so one of the pros is it's really easy to show groups of things as part of the whole. So here we have, how many? 1, 2, 3, and then there's 6 across. So there are 24 snails here in the group, in the whole. And we want to know each of these smaller groups, how much of the whole are they actually showing us? And we can get students to group parts. So for example, let's say C, I could get the students to draw like circles around 4 of each of my snails, and then count how many groups of 4 I have. And then think about if I have one of these out of how many groups. So you'll see if we count them, we've got 1, 2, 3, 4, 5, 6. And so 1 out of 6 parts has got to be that fraction here. And you can continue the same reasoning and logic for the rest of those collections as well. And maybe you would start, when you're scaffolding it with the first one, you've got 1 snail. So I've got 1 part out of how many? So that's 1 out of 24. So that would match this fraction here. Oh, this one's a great question that we got out of the literature, and it kind of shows how easy it is to confuse some of these ideas. And so you see a number of really interesting things. So a teacher gives some students strips of paper, and they have to show 1/2. And so if you have a look at these, have any of these students shown 1/2? I would say yes. Lila. So remember the definition of a fraction. It's got to be divided into equal parts. And 1 part out of 2 is shaded. So this is showing 1/2. But also I would say Jessie has shown 1/2. Because again, it's divided equally. Roland, these parts are not divided equally, so I'm skeptical about Roland. But have a look there's so many questions you can ask. This is 1/2, and then Jessie is showing 1/2, but it looks like Jessie's half is larger than Lila's half. You can ask students why. And the answer is because Jessie's whole is larger than Lila's whole. Similarly, if we consider Roland's strip and Jessie's strip, you can ask about, the same amount is shaded. Why isn't Roland's strip showing 1/2? It's the same amount. But of course, it's not the same amount because the whole is different, right? The whole between Roland's strip and Jess's strip is not the same, and so you cannot compare them. Remember, it's a requirement for fractions. Oh, these questions are really interesting too. So, one of the reasons why these are interesting as well is because they require some estimation, which, if you read and look at the neuroscience around how the brain works, a baby's brain actually is able to estimate really, really well. And the thing that we have to then teach is the more the precision basically of mathematics, that you can have exact answers and so forth. But we have inbuilt estimation. And this is what this question is doing. So it's defining the part and defining the whole. And we're saying, well, what fraction of the whole does the striped part show? And so it's 1/2 here, but they get trickier. And I haven't shown any of the trickier example, but you can imagine, right, if the part was smaller, a student would need to estimate how many of them they would need to make the whole, and therefore what fraction the part is showing. Oh, this question here again is now looking at going beyond the whole. So this is a point where students, can kind of get overwhelmed and not understand, well, what does it mean to have 4/4? Well, look at that. When you see a bar model and you define the whole as the whole bar, it becomes very easy to see the equivalence that 4/4 is the same as 1. Or similarly, that 8/4, I actually have shaded 2 wholes, so that's equivalent to 2. So using models to explore equivalence is really important. It gives you a really stronger conceptual understanding rather than using some sort of algorithm that seems like magic to kids. And here's another example. So you can use different types of shapes. Here, each of the holes is representing sixths. And so now we have what we call a mixed number or an improper fraction. And so we have 2 wholes and 5/6, which is the number 2 and 5/6. So again, we're connecting language models with the fractional notation. This is another misconception question. So here we have Nigella, and she says that, okay, I have 1, 2, 3, 4, 5, 6 parts. And so therefore the fraction that's shown here must be, I have 5 shaded, so 5 out of a total of 6. So she said this shows 5/6. And we want students to recognize, no, that's not true, because there are not 6 parts in the whole. In each whole, there are only 2 parts, and so my denominator for this fraction will actually be 2, and I can express this in different ways. I can say I have 1/2, 2/2, 3/2, 4/2, 5/2, so that's 5/2. Or I could even say that I have 1 whole, 2 wholes, and a half, which is 2.5. So look at that. This is a way of connecting an improper fraction with a mixed number in a conceptual way. We had no trick, no multiply this and add this kind of magic. It was a really easy visual way to connect the different representations. That's just a summary. And now we're going to talk briefly about fraction models. So I won't go very long into this, but these are some examples of the different types of fraction models that you can use to explain fractions and why they're good and why some of them I wouldn't use in specific instances. So an area model, so a bar model is an example of an area model. And they're very easy to draw. So that's one of their main and very easy to construct as well. Take a strip of paper and you can construct them. And they're also, it's probably out of all the models, the best one. The most, if you choose one model to use, this is the one that I would be choosing if I wanted to show my kids, some things with fractions and with a particular model. You can show equivalent fractions. So here I have 2 examples. And so here I've shaded 1 part out of 4. So that's 1/4. But now here for this one, I've divided it into 3 parts in the other direction. And so now I have 1, 2, 3 parts out of 12. So that means that 1/4 is the same as 3/12. Again, I'm not using an algorithm or any sort of multiplication. I'm just showing a model, using a model to show that equivalence. Here's another example, and sometimes like this isn't what's called a non-contiguous case, which means that the shading is not next to one another. But again, connecting the important one thing about this one is like we're connecting the language. What's the numerator? Well, it's the number of shaded parts. What's the denominator? It's the total number of parts, and so the fraction is going to be what? It's 3 over 12 or whatever it is. So circles, they have limited use, but you see them used in fractions a lot, probably overused. But one of the areas where they are really nice to use them is by constructing or converting between improper fractions and mixed numbers. So improper fraction, this is an improper fraction because I have each part is a quarter, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 quarters. So 11 over 4 is what I've shown here. But that is equivalent to 2 3/4. So it's a really nice way of, getting the kids to group them together. So to group the four to make one whole and continue going and see what you're left with. And the bar models as well, they're easy to draw and understand. They have many real life contexts that you can use. So here we've got Julia who bakes veggie rolls and she cuts them into equal pieces. And then we ask the kids about, different things that they can calculate that have to do with fractions here. They're also good for comparing. So this is the equivalent fraction stuff. So you see here down the bottom, we have the example. We've got 1/3 and 1/3, that's 2/3. What's that equivalent to? If I now have the same bar, but it's now divided into 9 parts, how many give me the same as 2/3? Well, it's really clear to just read that it's 6 over 9. And students need, they need practice with this and they eventually get the idea and they can then eventually generalize to an algorithm, but it needs to make sense, right? It needs to make sense why they're multiplying the numerator and denominator by 3 or whatever they're multiplying it by. And we saw this example before about, the equivalent fractions. You can split each part into more parts, which is what we've done here, but you can also go in the opposite direction. You can group parts. So here we've seen that we've grouped keeps on doing that. Sorry. We can group 2 of the rectangles here into one part. And so now this was 2 over 6. This is the same as 1 out of 3. So we can go in the opposite direction. And, for those of you who know the algorithm, people would say, oh, divide the numerator by 2 and divide the denominator by 2 and you'll get 1 over 3. But the visual way is so much nicer. And here we're talking about, defining the whole. We've talked about that before. So this is just, another good example that you can use. But notice here we've also used that circle example. It's really good for improper or mixed numbers. The bar models are also really good. We talked about this before for connecting with number lines. So we see here quite a number of examples. Look at this one. This is an equivalence one as well. So you see that 3/4 is the same as, if you think about it, 1, 2, 3, 4, 5, 6 eighths as well. So you can, having the bar there helps support the thinking on the number line. We can now use number lines to, and one of the strengths of it is it helps students think of fractions as numbers as well. And see here we are showing a mixed number on a number line. And you can use this for the conversion. So see here I've got 1 whole, 2 wholes, and 1/4. That's 2 1/4. But also I know that this is equivalent to, I know that each of the wholes is divided into 4 parts. So here I've got 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, 7/4, 8/4, 9/4. So I know now that 2 1/4 is the same as 9/4. And this is just a use open number lines. What that means is you don't necessarily need to start at 0 and finish at 1. Use whatever makes sense for a particular problem. This question here is really getting students to think about what fraction is shown by the dot. So Aria is ignoring, or sorry, Brown is ignoring where we're starting, and he says this is 1 whole and 2/3. So he's obviously incorrect because he hasn't considered that the number line starts at 5. And so Aria says, well, this is 5. I've gotten to 6, and then I have 2/3 again. So really, I'm at 6 and 2/3. And this is what I was talking about before. You can use them to convert. So here, there's a number of ways you can do this. You can count, you can go 1, 2, 3, 4, 5, and get all the way to 17. Or you can use multiplicative thinking. You can say, well, there's 5 parts in each whole. So I can count 5, 10, 15, and then 16, 17. So this 3 and 2/5, the other way I can write it is 17/5. Again, I'm not using an algorithm. I'm using a visual model to do this conversion. Sorry if you guys can hear my dog in the background. Um, and here again, we're using them to add fractions. So here, 4/6, it's a really nice visual way to see where you're going to end up. And you can subtract by just going in the opposite direction. The last model that I'm going to talk about is collections. And so here we're looking at groups of things, and it's really intuitive for students to define a fraction. So here we have 1, 2, 3, 4, 5, 6, 7, 8, but also we've selected 2. And if you think about grouping it into twos, you can think of that as 1/4. Um, there's again, it's very easy for students. They have a lot of intuition around collections. That was the example that we looked at before. But you need to be careful because sometimes with these collections, um, the whole is not clearly defined. So that's something that you need to be careful with if you're going to use collections with mixed numbers and improper fractions. So how do you define it if you've got, more than one, basically? That's it, really. I've kind of sped through that, but I think I don't want to bore people. But something, you can reflect on is whether you've noticed any of your children having these fraction misconceptions, and if there's anything that you could do differently. So out of all the examples that I've shown, have any kind of resonated with you? Would you consider using them to explain a certain concept? And, the last thing I really want to say is, if anything, I hope that I have convinced you to not just see fractions as another part of a textbook that I tick the box in and just move on. It's so critical that we don't do that with, certain areas of mathematics. Fractions is one of those areas because it does underpin a lot of what comes next, and it's really important to get it right to really maximize the opportunities for your kids in mathematics. The next page is just a list of references, but I'm happy to answer any questions that you might have now.
So I guess just to clarify then, talking about Maths Pathway as the program, it will continue to present problems to kids in varying fashions if you have a child like that. Again, I'm thinking of my child. It's just
Yeah.
going to keep presenting them back to them
Yeah.
until they're proficient.
Yes, we have a space practice kind of built into our program, but the other very nice thing is those gaps that we identified with students prior to them sitting our modules. I have more data that shows that all those gaps, they got filled with our students that did our sequence of modules. We went and we saw what's the up-to-date literature say about how I should teach this concept exactly, and that's what we've done. And you saw, like in the examples that I show you, like we don't just cover an idea once, we repeat it, we scaffold it, we start with a simple case and we get more and more complicated so that the student can really develop their thinking. And Kylie, that's actually one of the problems that, when you say, oh, somebody just doesn't get it, it's because they're missing gaps. They've got gaps. There's other things that they need to know first before they can get to a certain point, right? And sometimes as a teacher, that's what you need to do. You need to figure out, okay, what else don't you know that I'm assuming you know for you to actually be able to understand this? Um, like, their whole number knowledge, for example, if they don't know their times tables really well, then they'll really struggle with, forming the equivalent fractions, but they'll really struggle with the algorithm much more than these visual hands-on ways. So that's another thing that I would recommend is the hands-on kind of visual way really helps so many students that you have to take that kind of approach in my, in my opinion. For those who weren't here prior to us starting, Kylie and I were talking about careers and looking at, the most, you can find online lists of careers that have rankings based on, the job availability, income, and also stress levels. And the top, consistently year after year, when I check this list, the top jobs all require mathematics. And we would be doing a disservice to our kids and to kids everywhere if we were not giving them the opportunity to access those careers if that's what they wanted to pursue. I'm not saying that all kids want to, but I think our responsibility is to maximize the opportunity for them, to be able to access that if they wanted to.
Yeah, perfect. Well, thank you. Does anyone else have any other questions before we let Matty go? That was really, really very good. Thank you very much.